So for this particular question here now, it says the probability that Sam attends a certain sport activity is 0.4. Let's just say the probability of Sam in this way. So we'll see the probability of Sam going to an event is 0.4. And the probability that Betty attends the same sport activity is 0.5. So for Betty, we'll say Betty is equal to 0.5. The probability that Sam attends the sport activity given that Betty does is 0.7. So when we're talking about given, we're saying the probability that Sam attends. So Sam is gonna attend, but we have to consider that Betty is already there. So this is how we write it. So Sam given that Betty is there. This would be equal to 0.7. So this is the information that we have been given so far, which we more than likely are going to use to answer these questions. So the first question says, state two basic rules of probability. So one of the ones that I will talk about is the addition rule, and since we are using S and B, I'm going to use that here. So we have the addition rule, which goes like this. So we could either have Sam or Betty, which would be equal to the probability of Sam going to the sporting event, and we'd add that to the probability of Betty going to the event, but we'll subtract the intersection, which would be the point where both of them happen to go to the event at the same time. So we'll have to subtract this because it would have already been counted twice, because we would have counted the probability of the time Sam went as well as the probability of when Betty went, which would mean that this here would be added twice. So this is why we have to subtract it with this rule. So that's one rule. The next rule is we could have the rule that tells us what this is. So for instance, S given B would also be equal to the intersection of S and B divided by the probability of B. So whatever you have on this side here, we divide it at the bottom here. So if we had it the other way around, so if we had like P, B intersection S, we would have had the same intersection at the top, but this time we divided by the S. We could have also have the complement rule, which would mean that, for instance, PS is equal to 1 take away the probability of S. So that's another rule that we could have. We could have also have the intersection rule for when it's independent. We could have had a rule for when it's mutually exclusive. We could have had a rule that probability must be more than or equal to 0 or less than or equal to 1. There are different rules that we use in probability in order to answer probability questions. So these would have been the basic rules. These are the two that I chose to use. All right. Now the next question says, find the probability that both Sam and Betty attend the sport activity. Now when I'm looking at this, it's saying that Sam and Betty attend the sporting event. So we could have a situation where we have an event. I'll say this is an event. We could have a situation where Sam is there, but Betty is not. We could have a scenario where at this same event, Betty is there, but Sam is not. But we can also have a situation where both Sam and Betty, these would be two different situations occurring at the same time. So we could either have Sam alone and not Betty. We could have Betty and not Sam, but we want when Sam and Betty are there. Because they're going to a sport activity, they can be there at the same time. They can be there at the same time. So if you look at this, for instance, now, this first equation here gives us the opportunity to calculate that, because it includes the intersection, because that's what we are basically trying to find. What we are trying to find is the probability of Sam and Betty. Remember, this is an intersection, which means they're both happening at the same time. So Sam and Betty. Remember, in this case, it means Sam or Betty. Okay? So this wants us to have Sam and Betty. The only way we can do that is if we figure out the intersection. Now, we have a formula here, this first formula, that allows us to calculate the intersection. If we can rearrange, we have this value, we have this value. We are looking for this, but the issue is we do not have this here, so we cannot use this one. Now for the second one here, as you can see, we were given this one, which was Sam given Betty was there. So we have this here, we are looking for this, and we were also given this. So we only have one unknown in this situation. Therefore, we could use this to help us work out what the intersection is, meaning the probability when Sam and Betty are there. So let me write back this equation and try to rearrange it. So we'll have this here. Now, what we can do is substitute some values. So if I substitute this, I'll get 0.7 is equal to, we don't know what the intersection is, so we put this back, over, what is this equal to? That's equal to 0.5. Now, in order to work this out, I can put 0.7 as a fraction, and a number as a fraction is itself over 1. So as you can see here, we have 0.7 over 1. Now I can cross multiply. So I'll multiply the 0.7 to the 0.5, and then I'll multiply the intersection to 1. So then we'll end up with 0.7 times 0.5 is equal to P, probability of S intersection B, times 1. So 0.7 times 0.5 is 0.35. So therefore our answer, and this P S intersection B times 1 is itself, so we know that this is our final answer. So we just worked out what the intersection was. So we have a new thing to add to what we have up here. So now we could look at the next question. Find the probability that Betty attends the sport activity given that Sam does. Alright, so for this part now, what they are saying is that there's a situation. So I'll show you two ways. I'll try to do it in a Venn diagram, and then we actually do the mathematical calculations for this. So we have Sam here and we have Betty here. Now the reason why I joined them together is because we have an intersection. We know this because both of them can go to the event at the same time. So the fact that both of them can go to the event at the same time, I know there's an intersection. There's a chance that they can be there together. Now, if I'm looking at the probability of Sam, this entire circle here, it represents 0.4. However, we know that the inner part here, or the intersection, represents 0.35. So then, if that's going to be 0.35, we need to figure out what the section here that's Sam alone would add up to be. So, if the entire thing is what 0.4, that must mean that this section here would be 0.4 take away 0.35, meaning taking away the inner part that we have inside here. So we know this is 0.35, and inside this section here is 0.4 minus 0.35, which is 0.05. So we know that this piece here is 0.05. Now both of these add up back to 0.4. Okay, so that means the whole probability of S is 0.4. Let me change the colors of these circles. Alright, so we have this now. Now the next thing that we need to figure out is for B. So B is 0.5. So likewise, B would be 0.5 minus 0.35, because we got 0.5 from here, which would be 0.15. So just putting that out there in case we need it. Alright, so this question says that find the probability that Betty attends the sport activity given that Sam does. So whenever we're talking about a given situation, the first thing we have to look for is what's the condition we are checking for. So it says find the probability that Betty attends sport activity given that Sam does. So in essence, we are doing this. Betty attends given that Sam does. So the probability Betty goes, but Sam is already there. So because of that, when would there be a situation where Betty goes and Sam is there? So if we look at this, we can focus on that situation when Betty and Sam are there. When would both of them be there? When it has 0.35. Now, follow me here. So for the probability of this, the formula for this would be P S intersection B over the probability of, you guessed that right, S. So we have this intersection already, S intersection B. So S intersection B is 0.35, which can go over the probability of S, which is 0.4. So this 0.35 goes over the probability of 0.4, which would give us our answer for this particular question here. So this is equal to 0.875. If you think of it, what given is actually doing is checking the chances of Sam and Betty being there. But it's not just checking for the probability of Sam and Betty being there. It's checking for the probability that Sam and Betty are there, but during a time that we expect Sam to be there. So it's a focus on this particular event here, which is why we end up putting 0.35 over the total for Sam, which is 0.4. This is why this formula works that way. We are checking for the probability that Sam and Betty are gonna be there, but the condition has to be during a time that Sam himself is actually there, and the probability for that would be 0.875. So there's a 0.875 chance that when Betty goes to the event, Sam will be there. So that's our answer for this one. Alright, so for this last question, it says find the probability that either Sam or Betty attends a sport activity. So we're looking at the probability of Sam going or Betty. Alright, now how this is denoted in probability is like this. We have S, and this here symbolizes R, Betty. Now we had that formula earlier, okay, so we could use our Venn diagram to help us answer this, which we worked on earlier, which would be the total of all of these here. Okay, so we did the individual sections. So this section is 0.05. So if we go 0.05 plus 0.35 plus 0.15, that would give us 0.55. So this covers the probability that Sam or Betty goes. This situation here, because we have it in a Venn diagram. However, let's work it out using the formula as well. So the formula for situations when they are intersections, we looked at it right here earlier. So in essence, I could say that the probability of Sam or Betty going is the probability of Sam plus the probability of Betty minus the intersection of them going. And guess what? We have all of these now, so that we can use this. So we have this here, Sam or Betty, which would be equal to the probability of S, which is 0.4, plus the probability of B, which is 0.5, minus the probability of the intersection, which is 0.35. Now when we work this out, we'll end up with 0.4 plus 0.5 is 0.9 minus 0.35, and this would be equal to 0.55. So as you can see, I used two different approaches to calculate the same answer. Whichever one suits your understanding, this is what you would have to do. Okay, so we know that these were events that could occur at the same time, because there is a chance that these people would actually be can go to the event at the same time. Now this question is saying that it's known that the probability that a patient treated with a recent drug will recover from a certain disease is 0.85. So the probability is 0.85. So this here is for recovery from a disease. And that patient's reaction to the drug are independent of each other, so it doesn't affect the other. So when I'm looking at this already, I'm seeing it laying the ground floor for binomial. They're independent situations. We could either have two scenarios. You either recover or you do not recover. And we have to consider a random sample of 200 patients treated with this recent drug. So we have a cap on the number of trials. So if you go back to what we did in question 3, this qualifies for a binomial distribution. So you can review the conditions that we need for a binomial distribution to understand why this here is a binomial distribution. So this cap was a key thing for me. It has a cap 200. We have a probability is either yes or no situation, basically recovery or no recovery. And the next key thing, they are independent. So we have P is equal to 0.85, N is equal to 200. Now let's see what they want us to calculate. So they want us to determine the expected number of patients in the sample who will recover. Now, if you're looking at this question, the thing is, if I give you 200 people and I say, the probability of them recovering is 0.85. So in essence, what is 0.85? As a percentage, 0.85 is 85%. So if I'm expecting that 85% of the people will recover, that means that my expected value, or what we call the expectance, must be equal to the number of people multiplied by the probability of them being fine or recovering. So in this case, it would be 200 multiplied by 0.85. This here would give us the answer, which would be 170 patients. So this is our first question. Now, the thing is with this, right? Remember, this is the same thing as if I was telling you, remember 0.85 is basically like 85%. So just consider that expectancy is literally just like finding the percentage of the number given when it comes to binomial. Because when it comes to binomial, our expectancy is n times p. So if I had 200 people and I say, oh, usually 85% of the people survive this or recover, I would just say 85 over 100 times 200 over 1. So then that would give us 170. So one of the best ways to understand these concepts is just trying to make it practical, making sense out of the potential chaos. Alright, so number 2, it says determine the variance of the number of patients in the sample who will not recover. So they want us to determine the variance of the number of patients in a sample that will not recover. Now, when it comes to variance, the variance always surrounds the mean. And when it comes to the variance in probability for binomial distributions, the formula for that is usually NPQ. So N multiplied by P multiplied by Q. So it doesn't matter whether they say the sample who will not recover or the people who would actually recover. The variance will be the same just because we have to calculate it based on the N times P times Q. So in this case, it would be 200 multiplied by 0.85 times Q. Now Q would be 1 take away 0.85, which is 0.15. So our variance in this case would be able to approximate it as 200 times 0.85 times 0.15. For the answer for that would be 25.5. Now if you wanted to take it literally, now the variance is usually basically the expectance multiplied by whatever the Q is. So let's just say what would have been the expected value for the people who will not recover. So if we expect 170 people to not recover, we expect that the people who will not recover would be 30 patients. How did I get 30 patients? I just subtract 170 from 200. Now, remember, we are saying that to get this 30 patients, I literally had to multiply 200 times 0.15 if I wanted to, because this here would be not recovering. Remember, we said that this not part, the not recovering, would be 0.15, which is what Q is equal to. So I'm saying 200 times 0.15 would give us that value, the probability of not recovering. So 200 times 0.15 is 30. Now we need to multiply that to what? We need to multiply it to 0.85. Okay, because this is the probability of recovering. So even though we're focusing on not recovering, we still have to multiply it by the probability when it's recovering. So essentially, when we find 30 times 0.85, we still are going to get back the same 25.5. So our variance in this case, no matter how it's said, is the same exact thing. So then therefore we would have 25.5 as our answer. Okay, so for this last question now, it says to determine the probability that the number of recoveries in the sample is less than 175. So that's the first thing we must have, but greater than 160, and we have to use a suitable approximate distribution. So let's figure out what this here looks like first. So it says less than 175. It did not say equal to 175 or anything. It says less than 175 but greater than 160, not equal to 160 but greater. So we could say the probability, the lowest value is 160, and we're saying that X is more than 160, but it's less than 175. Now, the important thing that they told us to do here is using a suitable approximate distribution. Now, we already established that this here was a binomial distribution. This here was a binomial, and binomial can be approximated to the normal distribution. So when we say that it can be approximated to the normal distribution, we're converting a binomial to a normal distribution. Now, in order to do this, there's some rules that need to apply. So in order to convert this, n multiplied by p must be more than 5, and n times q must be more than 5. So in this case, n is 200 and 0.85 is the value for p. So these are the conditions that need to be made in order for the binomial to be converted into a normal distribution. So in other words, we could sit down here and work out every single one of these values. So 160 plus 161 plus 162 plus 163 plus 164 and so forth, using the same NCR formula that we used in our previous question in question 3. So if we do this, we could use this formula to do 161, 162, 163, straight up to 174. Now, if you look at that, that will take quite some time. It's a couple numbers that we have to do in order to work that out. However, this question is telling us that we could use a suitable approximation to do this. Now, the suitable approximation that we could use in this case would be a normal distribution once we are able to meet this criteria where NP is more than 5 and NQ is more than 5. We kind of did a calculation earlier that kind of helped us to realize that that would be the case, because N is 200, P is 0.85, and Q is 0.15. So if I do NP, that would be 200 times 0.85. So essentially, this is equal to 170. So therefore, in this case, we met this criteria. Now the next thing we have to check is NQ. So NQ would be 200 multiplied by 0.15. As you can see here, once we do that, we'll get 30. And once again, this is more than 5. So since these two conditions are met, we can approximate a binomial to a normal distribution for this particular question. Now, when it comes to approximation, we have the binomial that is written like this. So we have bin, which is NP. Okay, we have bin, which is NP. And then we have the normal distribution, which uses mu, or the expectance, as well as the variance. So previous question kind of set us up to be able to answer that. We have NP already, which can be used as the expectance, and the expectance is basically the same as this value here. This value represents the mean, which is another way of saying the expectance. So this is a mean, or mu, and the variance here is this squared. All right, so the standard deviation, the sigma squared. Now, if that is the case, I could basically say that if I'm converting this binomial to a normal distribution, I already know what mean is. In this case, it's going to be n times p. So the mean is given as n times p, also known as the expectance. And this here represents the variance, which is equal to NPQ. This here is the mean. So then now, for the normal distribution, for this approximation, I could say that it's going to be 170, comma, and then we're gonna have the variance, which is 25.5. Now, another thing that we need to talk about, once we're converting from binomial is discrete. So we discussed earlier in question 3 what discrete is, and we also have it converts into a normal, which is continuous. So in other words, if we want to convert the binomial to the normal, we have to convert these numbers here to represent continuous data. So let's talk about it. In the binomial world, 160 would be represented as one line. Okay, so in essence, 160 is a flat number. But in the continuous world, we will be using boundaries. So 160 is not just 160. There are values that can fall as 160, which have decimals. So for instance, you can have 160.3, that would be rounded to 160. 160.4 is the same as saying 160. So therefore, in a continuous world, we have to consider stuff as any value that we can get that is less than 160.5, and we can also get values that go as 159.5. So any value inside here can be considered 60. So think of it like this. If I was to have 159.8, you would say that is 160. That could be rounded to 160. If I had 160.4, this could also be rounded as 160. Now the thing is, if this was 160 in a binomial question, we need to figure out what less than, if this is the value in a binomial world, we need to figure out what. If this says x is more than 160 in the binomial world, we would say that is going this way. Any value that's higher than 160. Okay, so any value that's higher than 160, we can consider it. Any value that's higher than 160, we can consider it to be binomial, to be representative of x is more than 160. Now, in the continuous wall, since we're saying x is more than 160, we have to think of 160 being enclosed by these two boundaries. So therefore, anything that is 160 falls inside of here. Now what that means is anything that's more than 160 would fall outside this way. Okay, so if it's more than 160, we're talking about going from 160 to 161 and so forth. This here represents more than 160. If we wanted to say more than or equal to 160, we have to consider from this boundary here, because then now any value that could be equal to 60 would be within here. But for this case, since we want only more than 160.5, this is what we're looking at, more than 160.5. Since you're doing binomial to continuous, we have to convert it as well. So if we have this here now, we have to convert this expression here as well. So right now we have 160.5. So in the binomial wall, if we have this expression, it means more than 160. Now in the continuous wall, more than 160 would be 160.5 would be this. So now we have to do the same thing for 175. So we know what the first thing is for the continuous expression. So 160.5 more than. Now we need to figure out what value would go here to represent this part here. So see if you could figure it out by using this analogy here. So in the discrete wall, we have 175. Very strict number, has to be a full number. So less than 175 would be over here. Now from the continuous point of view, remember, even though this is 175, we have to include it being at this point here. So at this boundary, we have 175.5 and 174.5. So if we're saying that it's less than 175, we have to look at the boundaries. So in this case, less than 175 in a continuous wall would be on this side, because this whole bar here represents 175. So over here, we could say less than 174.5. Therefore, now that we converted it and we converted this as well, we can use this information to help us calculate from a normal distribution standpoint. So the process we just did, we call that a continuity correction, and we always do this when we converting binomial to normal distribution or any discrete distribution to a continuous distribution. Alright, so now that we have this, we'll do a similar concept to what we did in question 3. So we know that the mean is 170, and we have our borders here now. So we say we want to see when it's 160.5 and 174.5. So the data, we want to figure out the probability between here. So similar to what we did last time, we would work out what is less than 160.5 and also what is less than 174.5, and once we subtract these two, we will get the final answer. Now let's go to the bank, which would be the Z-score bank as we discussed earlier, and try to put this together. So let's clear the screen a little bit. So we know that the mean is 170, so I'll try to work out this one here first. So I would say that the Z-score is equal to x minus the mean divided by the standard deviation. So as you can see here, our Z-score would be equal to 174.5 minus 170 over, now the standard deviation has to be the square root of the variance. Remember, right here is the variance. So we divide this by the square root of 25.5. So when we work that out, we will end up with Z is equal to 174.5 take away 170, which is 4.5 divided by square root 25.5. So that would roughly give us Z is equal to 4.5 divided by 5.05. So this would work out to be Z is equal to 0.89. So when we check the probability for that, so we have 0.8 and it goes to 0.89. So 0.89, which is 0.8133. 0.8133. So the probability would be 0.8133. 0.3. So that's the first part. Now we need to figure it out for 160.5. 160.5. All right, so for this case now, less than 160.5. So 160.5. In this case, we do the same thing. Z score is equal to x minus mu divided by the standard deviation. We worked this out already. So Z is equal to 160.5 minus 170. And this would go over 5.05. So we got that 5.05 from our last question. So Z is therefore equal to negative 9.5 over 5.05. So our Z value is equal to negative 1.88. Negative 1.88. Now, similar to what we did from our question in question 3, because we have this here as a negative 1.88, because remember, in order for it to be negative on the Z score, it has to be on this side. We need to figure out what the opposite area would have been. So the one that would have been over here at positive 1.88. The reason why is, remember, we do not have the negative components of Z on our table that is given to us by the CABE exam. There is one that exists. It's just that they don't use it for the exam. All right, so we have to look for the one that has 1.88, which would basically show us the value of the area for this, which would be the probability for this part here. Now, if we could figure that out, remember, we could subtract that answer from 1 and figure out this area here, because this whole entire area is equal to 1. Remember that. So if here is what we can work out, we would know the value for here. Why? Remember, they are symmetrical. So let's look for 1.88. So 1.88 would be 1.8 here. Then we have 8 here. So 1.8, 1.88, which is 0.9699. So here is 0.9699. Therefore, area in here would be 1 take away 0.9699, which is equal to 0.0301. So therefore, our probability for in here, or for this piece here, is 0.0301. Now remember, we have that probability now as well as this probability, and we said that to work out the probability of in here, we have to subtract the probability of the two. So therefore, that would mean that our probability for the final answer would be 0.8133 minus 0.0301. So that would give us an answer of 0.7832. So this is our final answer for this question, 0.7832, which would give us the value for this question here. Hopefully that makes sense. Continue to work hard and try your best to stay focused, stay encouraged, so you can do good on your examinations.